My name's Stuart Aitchison and I'm here to teach ECE110. I guess you're here to listen to me. Okay. First, my apologies for yesterday. I ended up having an emergency doctor's appointment when the lecture was on, so I couldn't do both things. So we're starting off a little behind. However, this section gets videotaped and will be available online. And this is about the fourth year they've videotaped me doing all these lectures. So the introductory lecture, we will post last year's or the years before, so you'll have that information in the next few days. So my plan is today give a quick overview of the course and talk about electric chargers. So just by ways of introduction, maybe I can ask you guys, what course are you doing? Are you ECE or? Industrial. MSEs? So you're MSE Industrial. Okay, good. And well, I guess my background, just to give you a bit of background, I studied physics as an undergraduate many years ago. I've worked always in electrical engineering departments on optics, nanotechnology, micro nanotechnology for telecoms applications, and more recently for biosensing, portable point-of-care devices for taking lab quality tests out into the field. And I guess just by way of introduction, a lot of what we'll talk about in this course is fairly old material. So Coulomb's law we'll talk about today, that's from the late 1800s. We'll talk about electric charge, magnetic fields, electric fields. So the first part of the course up until reading week is a sort of physics course. It's the introduction. And you might think, well, what's the point of knowing all this stuff? And I guess we still use a lot of this stuff in common devices. In research, there's a lot of work on microfluidics, lab-on-a-chip devices for moving blood samples around, the blood flow is controlled by electric fields, which are controlled by capacitors on the chip, something we'll learn about here. You can sort cells by tagging them with magnetic particles and then using magnetic fields to shift particles into different flow streams. So there are many examples of the technology or the ideas, the concepts we'll talk about, which appear in modern research. So it's not all outdated, old-fashioned stuff. The concepts also underpin what we'll talk about in the second part of the course. After reading week, we'll get more into electrical engineering. We'll do circuit analysis. We'll look at resistive networks. We'll look at capacitive, inductive networks. We'll look at transients. And we'll look at some work on alternating AC circuits. So that's basically a brief summary of what we'll talk about. So I guess by show of hands, anybody come across electric fields before? Electric charges? It's not a new concept. Okay, so maybe the first few lectures will be revision, background, catching up, relatively straightforward things. So what else do I want to say? I guess I should write my name down so you've got a note of that. So my name is Prof. And my room is Galbraith, building 434. If you need to get me, we'll post office hours in the next week or so once we get going and timetables firm up, etc. I also coordinate the whole course, so I'll try and keep this section in line with all the other sections we're going to run. Talked a little bit about part one, part two. What else do I need to say? Mark distribution, always an important topic. We want to talk a little bit about how we assess the course, because that tells you how to work things. So I guess we've got a number of different assessments. We're going to have some online assessments. So these are Wiley Plus type assessments. And if you look at the website under course material, you should see a link to the Wiley Plus. And there'll be, I think, 7 assessments that are graded, and they'll give you about 10% overall for the total course. There's also Assessment 0. Assessment 0 is live now. It's really for you to practice using the interface. So I encourage you to go and log on. Some very simple problems there, and it really is inputting, outputting different things. So you know how to use the interface. The tests will appear in sync with the courses, and they'll cover everything that we're covering in the textbooks. Everybody gets the same question with different numbers, so you have to work out your numbers, so you can't collude in that sense, so they're all going to be individuals. I encourage you to talk to your colleagues about how you do the problems. It's interactive. I look at the Wiley Plus as learning to do problems. It's part of the overall learning for the course. We also have labs, so there's a practical component to this. So the first labs will cover electrostatics, then there'll be introduction to electrical equipment, and then some magnetic fields, and then some network type labs later on. So I think you've got 5 labs, and that's 15%. We have 2 class tests, which will happen on February the 13th and March the 20th, 2018. We've now updated the course description, so we do have 2 class tests. They're worth 15% each, and then a final exam of 45%, which will be scheduled sometime in April. And I guess we don't do that, the registrar's office do it, so I don't have a date for that yet. Okay, so there's different ways of learning, or different learning components there. And one thing I would encourage you to do, and I encourage all classes that I teach to do this, is the textbook has got all the information you need in it. It's a textbook, it's in edition 11 or 10 now, whichever version you've got. All the errors have been removed. It's a good, relatively good textbook. It's easy to read, it's descriptive, it's got the math in there, it's got lots of work problems. So I would encourage you to read the textbook or the appropriate chapter before you come to class. Okay with that? So if you're doing Shakespeare, I wouldn't write Shakespeare's works on the board and you wouldn't sit there copying them down. You'd have read them and then we would discuss. And that's a much better way of learning. So I'm not going to rewrite the textbook. I'll write the main points that I want you to keep in mind. And as any transposition exercise, there'll probably be additional errors and mistakes, and I encourage you to call those out, because it's hard to see the blackboard when you're so close to it. So I will try and summarize and discuss, give other examples, talk about the work in a different light, different ways of looking at the same thing, but it's assuming that you've read the textbook or looked at the textbook. So there's only a few pages per lecture to read, so it's not a huge amount. So I encourage you to do that reading ahead of lectures. And the tutorials are tutorials, and you know, a lot of people go and then a lot of people think, well, I don't need to go to tutorials. I go to the lectures and learn everything. But sure, it seems easy when I talk about it and explain it here, but when you have to implement or do problems yourself, it's much better to have practiced and have some ability to do those problems. So the tutorials are another important component. So I'm encouraging you to attend all those tutorials. The TAs will review what we've been talking about. They'll give practice examples. They'll also have additional examples, additional material, and they'll help solve problems. They'll help you solve the problems that you need to solve when you come to the midterms and when you come to the final exams. And that's sort of participation. And it's important because, does anybody play hockey here? Any hockey players? Anybody, any musicians here play an instrument? Okay. So how do you learn to play your instrument or play hockey? You don't go to lectures and listen to somebody talk about notes or strategies on the ice. You go practice. And that's what the Wiley Plus stuff is for, and that's what the tutorial's for, and that's what the labs are for. So it's that practice, the participation. So the more that you dedicate to this course, and other courses of course, the more you'll get out of it, and hence the better grade at the end of it. So I encourage you to be active participants. Okay, any introduction? I think that's probably good for introduction. So let's talk a little bit about the first topic, and that's electric charges. And if you've done any chemistry or material science, you know that matter or material is made up of atoms. And atoms are made up of electrons that surround the nucleus, and the nucleus has got protons and it's got neutrons in it. So essentially you've got a negative cloud surrounding a positive nucleus. So that tells us that matter has some property of charge. There are charges there. Most of the time we think that everything's neutral because number of electrons equal number of protons, there's no charge, and everything is in equilibrium. The electric charges, the electric fields, and the forces that we're going to talk about arise from the fact when we begin to separate those charges. We perhaps remove some electrons from a material. So if we remove some electrons, which have a negative charge, from a material, that material becomes positively charged, and we have some negative charge that we've removed, either by rubbing with something, and you'll do some of these experiments in the lab, or various other ways of removing charge. So let's just start with some basic definitions. So matter, or let's just say atoms. And we'll say atoms, they're the basic constitute of matter, be it conductor, insulator, etc. Composed of electrons. And these electrons have a negative charge. Anybody know what that charge is? See, by the end of this, I want you louder. So I'm thinking I'm hearing the correct answer. So the charge on the electron is E is 1.6 times 10 to the minus 19. And the units of that charge are coulombs. We measure these in coulombs. So the elemental charge on one electron is 10 to minus 6 coulombs. We also know, I guess, just as an aside, we'll write some notes later, but charge is quantized. So this is the smallest amount of charge you get, one electron. So 1.6 10 to the minus 19 coulombs, that's the charge on the electron, or magnitude of the charge. And we can't subdivide that. We can't make it smaller than that. We can have more electrons or more protons, so we can have larger charges. So this charge is actually quantized. So we can also say that charge is what we call quantized. Anything else at fundamental level that we... Well, the discussion has said we have atoms, and they've got electrons and protons. What we don't do in any of the experiments that we'll do in this course, or any of the electrical engineering things that we do related to this, is we don't create charge. We don't create new electrons. And that says basically the number of positive or negative charges is conserved. We may move them around. We may rub a surface and take positive charges and put them over here and leave this negative, or vice versa. We may move charges, and we may create distributions of charges on conductors or insulators and look at electric fields, but we don't create any more charges. So another thing we want to note is charge not only is quantized, but it's conserved. So charge is conserved. Okay, so those are sort of important points to make. Next thing we want to sort of look at is see if we can actually a bit more math underneath this. Can we understand what's happening? So we're going to consider for a moment Coulomb's law, and I think most of you have probably met that in the past. It's basically the force between two charged particles. And the original Coulomb's law came out of experiments. We'll see later in the course we can actually quite readily derive Coulomb's law from something we call Gauss's law, which is something we'll talk about a bit later. But if we do some very simple thought experiments, and these experiments were done with sort of quantities of charge, very small objects, pith balls on very fine strings, and forces were measured by deflection and calculated using the weight of the ball, etc. But let's just consider that thought experiment. So let's consider the following. And we'll consider point charges. And when we say point charge, a point charge is just one point in space, no particular size, all the charge is located at that particular point. So let's consider a very simple experiment. We're going to have two positive point charges. And we'll say this is plus Q, and this one is plus Q. So one of those is fixed in space, and we bring the other one closer to a certain distance away. Let's call that A. What early experiments were able to note is if the charges were the same, positive or negative, the force between those charges was repulsion. Yeah, I know you know this stuff. It's the force is away from each other. So let's see, we've got some color here. We can add a force on here, and we can say, well, this force is pointing this direction. There'll be an equal and opposite force on this one. We'll be pointing in that direction. So this charge sees a force due to the presence of this charge, and it's repulsive. It's pushing in the other direction. Likewise, this charge sees a force due to the presence of this charge, and again it's repulsive, so it's pushing in opposite direction. Same happens if I have two negative charges, perhaps two electrons, again separated by distance A. This is minus Q, this is minus Q. I would have the same forces. And these are vectors, so they have a direction. And of course, the final experiment, because we have both positive and negative charges, we have electrons, or we have an absence of electrons, so we have negative charges, or an absence of negative charge is a positive charge. We can have the condition where we have a positive charge, plus Q, and negative charge, negative Q. Again, we can call that A. This time we get an attractive force, so the opposite charges attract each other. So in this case, we'll have forces pointing in these directions. So this is just schematic. We're just showing where these forces are directed. So Coulomb had carried out a series of experiments looking at this type of things, and he noticed this type of arrangement. So like charges, positive and positive, or negative and negative, repel each other. Opposite charges attract each other. The other thing he noticed was the size of the force. If you bring those charges together, the size of the force goes up. And it goes up as 1 over A squared. So as A gets smaller and smaller, the force goes up. So it's like a gravitational traction. So they've got two masses far apart. So there's a gravitational traction as they get closer together. Depends over 1 over R squared. So that allows us to write Coulomb's law. So and there's a couple of different versions in the book. There's a vectorial form that says the force is equal to, and we have a constant k, which we'll come back to in a second, Q1, Q2 over, say, A squared, separation. And then there's a unit vector, something that tells us what direction. So this thing tells me direction. So it could be along the I, J, or some other axis. You also see the magnitude written as, so the magnitude and that's written as force equals, and I'll write K in a different sense in terms of basic constants. That's 1 over 4 pi, a thing called epsilon naught, which we'll define in a second. Again, the magnitude Q1, Q2 over A squared. So this basically tells us everything we need to know about forces on charges. So we need to have two charges. We need to know their distance, or their separation, A in this case. And there's a bunch of constants which make force equal to charge and distance. So we've introduced a new term here. So where can we go? So let's go over there. So where this thing epsilon naught, you know what this one's called? Maybe? Permittivity. This is the permittivity. And epsilon naught is 8.85 times 10 to the minus 12, and then it's got units of Coulomb squared, Newton meters squared. So I guess you can get that. The units is coulombs, distance squared, newtons, so epsilon must make up the difference and make the dimensions equal. So again, this is a number, if you don't already know it, along with E, are things that you should memorize. For a point of information, the calculators that we recommend, and every year I get to just before the exams and then people figure out that the calculators we recommend we do for a reason. They have these constants programmed into them. So if you need epsilon naught, I know the Casio one, you press constant and some numbers, it'll give you epsilon naught, so it's already stored in there. They also do simultaneous equations, they do complex numbers and other things that we'll use later in the courses. So it is worth knowing that the calculators do have quite a bit of functionality built into them. But I believe these are in the Sharp calculators as well. Certainly in the Casio one I have, these numbers are already stored there. So just as an aid. Okay, so we can now work out a force. And we know the force is a vector. And okay, the introductory lecture was on vectors, but you're mechanical engineers, so you're used to forces and directions and things, so that's you'll find this bit relatively straightforward. So if I've got two charges, I've got a force on A due to B and on B due to A. If I've got three charges, what happens? So for multiple charges, I just work out the component forces. So for multiple charges, let's clear some space. That's right. So for multiple charges, and maybe that you could consider as having Q1, another Q2, and Q3, which would be a negative number. So I've got 3 different charges. If I can solve this problem, I can solve this problem. The forces are conserved, so I just have to add up the forces. They're vectors, so they've got direction. I need to account for the different directions. But if I do that, all I do is just consider the total force. So for example, if I wanted total force so for the exam question, it says, what's the total force on Q2? Well, what do I need to know? I know there's going to be a component because it's interacting with Q1. And I can predict which direction that goes in. They're both positive, same, so they're going to be repulsive. So there's going to be a force this way. And this would be F1, 2. And this we could say is F2, 1. Force due to 2 on 1. There's going to be a force on due to the presence of this charge. That's going to be attractive because they're the same. So there's going to be a force pointing down this way. So this is going to be F3, 2. And there's going to be one up here, F due to 2 on 3. So now I can work out the total force on particle 2. It's just going to be F12 plus F32. Add those together, 2 vectors. Clearly is going to be something pointing in this direction. So the total force, I don't know, maybe I've got one more color. So F total is going to look like a vector like this. So again, I just apply Coulomb's law. I know 4, I know pi, and I know what epsilon is. Usually given these 2 quantities, I'll be given values for separation, so I know all the numbers here. I need to figure out directions. Is this along the horizontal, the vertical, or a particular angle? So I need to work out the vectorial component. And then I just add up the totals. So for multiple charges, total force which we can call F total equals F1 plus F2 plus. So however many charges you've got, you can add up the individual forces due to the different combinations. So one more definition that we want to make just while we're talking about individual charges. And that's how we define a quantity called electrical current, which essentially is the flow of charge. So we want to consider the flow of charge. So very simply, let's think of a pipe. And we've got some positive charges and they're flowing along that pipe. And we can measure that flow. And we measure the flow by counting the number of charges and using a stopwatch to time the length of time it flowed. So the flow of charge, which we call our current, electrical current, is defined as I for the current is just equal to, right in a differential form, dq, number of charges that pass during a particular length of time, by dt. So we'll come back to current a lot when we start talking about resistive electrical circuits. It's one of the parameters that we concentrate on, the flow of charge around electrical circuit. But we already said charge is conserved, which leads to one of the laws that we'll use to analyze circuits, i.e. total currents flowing into and out of a junction point in a circuit are conserved. We don't create new charge, so total flow of current is also a conserved quantity. So this basically says count the number of electrons in a known length of time, divide the two numbers together, I get the current. So we relate current, so we can say the units of this, 1 coulomb, which is this, dq, is just equal to 1 amp, and this is current, 1 second. So I've got a current of 1 amp flowing for 1 second, I have 1 coulomb of charge passing. That's a very large current flowing for a short period of time, so that's a large amount of charge. So we'll come back to this later when we start talking about electrical circuits. So how are we doing? Okay. Continuing our sort of introduction and definition, we need to define two different types of material. We need to define insulators and conductors. And as their name suggests, conductors conduct electrons or conduct charge. Insulators oppose the conduction of charge. And the simplest thing is an electrical wire. If you cut through an electrical wire, along the center there's a metal connector along the center. That's the conductor, that's where the electrons flow, that's where the high voltage is confined. Around it, there's plastic or rubber or some insulator, and that stops you from getting electrical shock. When you hold the wire, it prevents the flow of electrons out of the center. So charge behaves differently in a conductor and within an insulator. We just want to spend a couple of minutes defining that. So conductors. Basically materials which allow the free flow of charge. Typically metals would be a good class of conductor. And an insulator well, that prevents the free flow of charge. And that sort of rubber, plastics would be examples of insulating material. This doesn't mean that we can't charge up an insulator. We can still charge, we can add charge to it. It's just the charge can't move around once we add it. In a conductor, we can charge, we can add charge to the conductor, but the charge is free to move around. So that leads to a number of different scenarios that we'll look at when we define electric field and other topics in the coming lectures. But let's think of a very simple example. Let's think of a shell. So I just basically take a continuous shell, three-dimensional surface, and I have two of these. I've got one made out of plastic, one made out of metal. So let's consider two shells. So I'll draw it as a circle, but that's a section through a 3D. And this one's made of metal. And over here we've got another identical size shell, which is plastic. And now I come along with a transfer wand or some way of transferring charge, and you'll learn about this in the first lab. If you charge up something, you can create a charge on one surface. You can transfer that to another surface. So let's say I come along with this and I have some positive charges. Let's say I've got 3 positive charges and I add them to the shell. Those charges don't move. They're pinned. They're not allowed to freely move. But they're on the surface, or they're just where I left them on the shell. So the total charge on this shell is 3 times the unit charge I put on. So if each charge was 1 E, 1.6 10 to the minus 19, I'd have 3 times that on the shell. If I place the same 3 charges at the same point on the metal surface, what happens? Well, metal is a conductor, so the charges are free to flow. They don't stay in the same place. What do we know from Coulomb's law? Those 3 charges, if they're all the same, they're all going to repel each other. So where do they want to be? As far away from each other as possible. So on the metal surface, they would end up, let's say, up here, down here, down here. So the charge distribution is different. The total charge on the shell is the same, but the distribution is different. So that's the key difference between a metal or a conductor and an insulator. Insulator, you place charge on the insulator somewhere and it'll stay where you left it. On the conductor, it'll move, it'll try and get to the minimum energy type situation where all the forces are minimized and the charges are as far away from each other as possible. Okay, so let's finish up then with one sort of concept question for you to think about. So let's consider 2 points where I can have charges in space. And we're going to call them, let me just make sure I get this correct, A and B. So this is point A, and this is point B. And they're separated by a distance of A. So I know the separation, and I know the locations in space. So on this point A, I place a charge of Q on A is plus capital Q. So I've got a positive charge on this one, and Q on B initially is going to be 0. Okay, so I've got one charge and I've got another location, but I've not put any charge on there. So what's the force on B? Anyone else? I apply Coulomb's law. 1 over 4 pi epsilon naught Q1 Q2 over A squared. The force on B due to A or on A due to B is 0 because there's no charge. I need 2 charges to get a force. So if there's only 1 charge, there's no force. So force on B equals 0. No force. Okay, so next thing I do, and this is, I'm going to draw it along here. So the next thing I do is I take A and B, and I connect them together with a conductor, a short piece of wire that allows the free flow of charge. So this is a conductor. First concept, what happens?
Does the charge move from A to B until it equalizes?
Yeah. Basically, the charge will equalize. We assume symmetry, and you'll see a lot of problems that say assume some degree of symmetry. Unless it says otherwise, assume it's symmetrical, i.e. that if this has got a charge of Q, and I connect it to an identical point a distance away, I'm going to equalize the charge. So after I connect these together, the charge here is going to be Q over 2 and Q over 2. So now I remove the wire, I've got two charged particles. So now I can write down an expression for the force on these. So the force, again, I'm going to use Coulomb's law this time. For the magnitude of the force, it's going to be 1 over 4 pi epsilon naught. That bit's all constants. The charge on A is capital Q over 2. Charge on B is Q over 2. The separation, well, I guess we're given it over here. We haven't moved the points, so again, it's still A, so that becomes A squared. So you can rearrange that bit. 2 times 2 there is 4. That's over, so that becomes 16. So that would be 1 over 16 pi epsilon naught Q over A all squared. So you can begin to derive an expression for what the force between those 2 points are. So all we've done is taken the same points. We haven't added any charge. We've just redistributed the charge in this system. And the point here is Q, one of the charges is 0, so the force is 0. I redistribute the charge. I've got the same total charge in the system. I've just redistributed it. I now have a net force between those 2 points because I've redistributed the charge. The final point, the final part of the question, I'll include only because it has another concept for us, and that is I take B and A, and the problem says I then ground or I earth point A. So what does that mean? I basically take a wire and I connect it to the earth. This is a concept that will come up again and again, and it's worth spending a couple of minutes just talking about it. We assume that the earth is very large compared to anything that we're doing experimentally, and it's electrically neutral. There's so many atoms in the earth that all the positives equal all the negatives. So there's 0 charge there. So it's a sink. And because it's such a large 0 charge, if I connect anything to that, it also becomes 0 charge. It leaks away maybe 3 or 4 electrons. In the scheme of the size of the earth is nothing. So I assume that that's 0. So when you see the terms grounding or earth, it means I'm connecting something to basically a sea of electrons, and I'm essentially either pushing my negative or positive charges into there, and I create this becomes charge of 0. So this is called grounding or earthing. And it becomes important when we start looking at electrical circuits. In electrical circuits, we have voltages and we have currents flowing around. To simplify, we need to set some voltages to 0, and we do that by grounding. And we say that the earth has a 0 potential, so everything is measured relative to that, so I don't have to measure delta V's. So if I ground point A, without the wire there, we know that Q on B equals Q over 2, Q on A now goes to 0. So the charge on this, the original point that had all the charge is now 0. So I momentary ground, I remove the ground, and the final question is, what's the force on B? 0. To get a force, even though this one is, the point here is it's now got a charge, but there's no force on it if there's not another charge to interact with that force. So the key concept here is you only have a force between two charged particles. If you've got one charged particle and one not charged particle, there's no force, no electrical force. So in this case, no electrical force. There's only a force when I connect them together and give them both a charge. In this case, equal charges, but they could be different. And here again, I've made this one 0, and this one Q over 2. Again, there'd be 0 force.
If you remove the grounding, A remains 0?
Yeah. Yeah, so the idea is when this has initially got a charge of Q over 2, I connect it to the ground with a conductor. All the charge moves into the ground. And then I remove the conductor and I'm set at 0. So I assume I make a definition that the Earth is so large that anything I connect to it gets 0. And you know that if you've got electrostatic heating at home, if you've got forced air heating at home at this time of year, you charge up, you touch something metallic, you ground yourself, there's a spark, and your potential goes back to 0, but the charge that is accumulated on you because of the flowing air and the charged particles in the system has built up. Likewise, if you've got a fleece or something that's got plastic in it and you take it off, you charge up and then touch it. In my case, I've got cats. Stroke the cats and they spark because it's that time of year. Anyway, that's all I've got. So any questions? Yeah. No, I've removed the conductor here, so I just use the conductor to equalize the charge, then I remove it. Yeah, I go from there to there to there. The problem has got more steps in it than it is in the textbook, so it's